So how do we improve on the Bohr model of the hydrogen atom? Well, the development of quantum mechanics, the improved theory that we use today, was developed after a series of discoveries that we're going to look over in sections 4 and 5 of chapter 6, and that I'll talk about in this talk. And then we'll see the application of that to the structure of electrons in atoms in the following lecture. So in this lecture, we're going to be reviewing some of the historical developments, and there's at least one very important equation here that you'll need to know. So the first development has to do with the idea developed by a French scientist with the name Louis Victor Pierre Raymond de Broglie, 7th Duc de Broglie, who in 1924 in his doctoral thesis asked the question, if light, which we used to think of as being wave-like, really acts like particles when it interacts with matter, is it sensible to think that matter, like little chunks of matter like electrons, can they behave like waves? Well, of course, I wouldn't be bringing this question up if he did not arrive at that conclusion. He not only said that it was possible, but he worked out what the wavelength of matter would be. Now, it's important to understand here, this applies to matter, not to light. And the key here is that this is a mass. So this equation says that the wavelength associated with a piece of matter is equal to some constant, Planck's constant, divided by the mass of the chunk of matter times the speed at which it's traveling. And this was found, in fact, to be so important that de Broglie won a Nobel Prize for it in 1929 after it had been confirmed. And in fact, this is the only case I know of in history in which a doctoral thesis of a PhD student won a Nobel Prize. In fact, this was confirmed, believe it or not, by a very clever set of experiments done by Davison and Germer in 1927, in which they used electron diffraction. Single electrons diffract with themselves, and that's a wave-like property, and they were able to prove this experimentally. And so clever and important was that experiment that it led to yet another Nobel Prize in 1937. Okay? So let's see an application of the de Broglie wavelength formula, which you will definitely need to remember. Let me just emphasize, you need to know this equation. Okay, let's look at an example. What is the de Broglie wavelength of an electron traveling at 5.72 times 10 to the 6th meters per second? Well, we're going to use the de Broglie wavelength equation. Lambda is equal to Planck's constant divided by the mass times the speed. And since the question asks for the wavelength, it's already set up in a form that we can use. We just have to put in Planck's constant. You have to look that up. I would provide you with this constant on a test. In fact, any constant we ever use, I will provide on tests, except when I say in lecture that you need to memorize this as a constant, and I haven't said that about this. Again, the mass of an electron, that's a constant, a fundamental constant of nature. You can look it up in the back of the book. It's 9.11 times 10 to the minus 31st kilograms, and I'm using kilograms for an important reason, because, of course, we know in SI units, if you use SI units for everything going into an equation, you're guaranteed to get SI units out, and so then I don't have to worry about what my units are in my final answer. And then I multiply this by the speed, which is given in the problem, 5.72 times 10 to the, 6th meters per second. Everything is in terms of SI units in the equation, and so I know that the result is going to be in SI units of length, and I get 1.27 times 10 to the minus 10th meters, because that's the SI unit of length. And I could equivalently write this as 1.27 angstroms, remembering that angstrom is 10 to the minus 10th meters. And keep in mind, 1 angstrom is on the order of magnitude of the size of an atom. So we're saying that the wavelength of this electron is about the size of an atom. That's why it matters, because the wavelength predicted, generally these wavelengths are very, very small if the mass is big, because h is such a small number. But if the mass is tiny, like the mass of an electron, then you can get a wavelength that is appreciable in size. Now, if little chunks of matter, like electrons, act like waves, so that they have a wavelength, which means the distance between consecutive peaks, in some sense, the chunk of matter has to be spread out over some distance. So what sense does it make to say that an electron is located at one particular point if it has to be spread out over a region in order to define what a wavelength is? And the answer to this question, unfortunately, is it can't be located precisely. This, by the way, is a picture of Heisenberg himself. Heisenberg came up with a very important Heisenberg uncertainty principle, which is something that you should know because it's a fundamental pillar of quantum mechanics. Heisenberg uncertainty principle says it is fundamentally impossible to simultaneously, that is at the same time, measure both a particle's position and its momentum with arbitrary precision, that is, without built-in uncertainty. Notice this is a fundamental property of matter. It's not a statement about the precision of our measurement instruments. This is how matter works. And in fact, you can work out an equation. We're not going to use this to calculate anything, but to give you an idea, the uncertainty in the position, in this case, this is delta means uncertainty, times the uncertainty in the momentum, you can show it always has to be greater than or equal to h, Planck's constant, divided by 4 times pi, which may seem peculiar, but this is a fundamental rule, and as far as anybody has ever observed, no matter ever breaks this rule, ever. So important is this. Again, we see a Nobel Prize for Heisenberg in 1932. Finally, putting this all together, another German scientist, Erwin Schrödinger, this fellow over here, developed a rather sophisticated mathematical model based on wave equations, and it is really quite complicated in terms of the math, but we have a very simple way of showing what we call the Schrödinger equation. This is the generic form of the Schrödinger equation. This h with a little hat on it, that's something mathematically called an operator. When it operates on this, which is called the wave function, it gives the energy, which is just a constant, times the wave function. Now, it looks at first blush like this is some sort of equation where you could just cancel out the h hat and the e on both sides, but you can't do that because the operator is actually a rather complicated mathematical thing. I'm going to show it to you briefly. Please don't worry about memorizing it. It's just to give you the impression that this is some sort of combination of partial derivatives of functions and constants. It's messy. It's not just a multiplicative sort of thing. We're just going to get rid of that because we don't need to use that in this class. I'm just trying to convince you that this is a little bit more complicated than just some constant times a function. So Schrödinger won a Nobel Prize for his work in 1933, and this is the model that we're going to use for atoms to describe things, and we're going to see some of the results of this in the next lecture. So the solutions to this equation, the Schrödinger wave equation, that's what SWE stands for, Schrödinger wave equation. This is a function that describes the electron completely in the region of an atom. And one of the main physical implications of the function is that the probability density, the likelihood for finding an electron per unit volume, that's what I mean by probability density, probability per unit volume for locating the electron is given by the square of this function, which seems, mathematically crazy, but it actually works. It matches up with experiment. And we're going to see some of the conclusions from this that will help us understand the behavior of atoms in the next talk.